So I have to admit, I'm unusually nervous about this one because this is a lot different from the normal talk, and actually from a lot different from the talk that Tom originally invited me to give, which was just going to be about Isolde and where it's at. But the more I thought about it, the more I realized that it's, I wanted to talk about something that's been really growing in my mind a lot. And it's going to sound very strange coming from me, that where I've spent close to 10 years now working on ways to make interactive model building easier, faster, better. I think it's becoming more and more urgent that we essentially make me obsolete and really get to fully automated model building. And I'll go through the reasons behind that, but ultimately it's lovely to have exponential growth and very fast exponential growth of Graham structures in the PDB. But the problem with exponential growth is that it has a habit of turning looming problems into very suddenly very big problems. And it's time we head that off before it really becomes huge. Anyway, the good news, of course, automated modeling tools continue to improve and at a remarkably rapid rate. So, of course, AlphaFold changed everything a few years ago. Model Angelo changed everything again, really quite recently. There's also the work that the Phoenix team have been doing, iterating auto building with AlphaFold, getting really quite good fits to a map in a fully automated manner. But nevertheless, at the moment, the golden rule, originally coming from the Richardson lab, I believe still holds true. Human eyes should see each residue in density at least once. Now, the problem there is that it's becoming, well, it's almost impossible to prove, of course, but it's becoming more and more apparent that should is doing a lot of work in this sentence. And there's no, it's not really surprising as such. It's models are getting big. We're getting them faster and faster and faster. And there are so many pressures on our time. And there is a lot of evidence really to suggest that for a great many models, either the golden rule was not followed, or more generally, the human eyes in question, it was their first model. They're not used to looking at maps. They don't know what a nice looking fit is. And it's totally understandable. I mean, as I said, structures are getting bigger. And for modern papers, it's almost becoming almost vanishingly rare for a structure to be the sole focus of a paper. It's one part of a much, much bigger body of work. And newcomers to the field, I think, often naively expect the automated building and refinement to do a lot more than they actually do. And confession of mine, back in 2015, when I first submitted this little thing for paper for publication, I was a complete newcomer to structural biology. I had no formal training by anybody. But I come across this problem, the cis-peptide bonds not going unflagged and becoming more and more common in deposited structures. And in my first version of the paper, I blamed Phoenix Refine. I figured, okay, that has to be where this is happening. And it was very gently pointed out to me by a reviewer that that's absolutely impossible because the refinement tools just don't do that sort of rebuilding. But yeah, these sort of problems are very, very common and are only going to become more common as we have more and more people moving into the field and with less time to actually really learn the way the original crystallographers learned over by painstakingly building models by hand. So ultimately, I think it is time to go the rest of the way. That human-intensive model building and validation is rapidly becoming a really unsustainable problem. Sorry. Oh, wait, Jesus. Sorry, I've already been through that. A few of the other issues here. I mean, the pressure to publish is constantly putting perverse incentives on us. We're always in a rush to go forward. And the fact is that once you get past a certain point, nobody is giving you any reward for perfecting your model, for spending that final time to really polish it and make it perfect. And there are de facto rules of thumb everywhere about what is good enough in the people building the models, in the people reviewing the models. And so people are asking themselves, okay, do we have few enough Ramachandran outliers? Is our clash score low enough? Is it good enough to answer my specific biological question about the active site of my complex? Or most dangerously, is it good enough to get past peer review? And that's the most dangerous one, because the answer is always yes. So this one, I'm not going to name this one here. It's a subject of a bit of controversy at the moment, but ultimately, well, it manages to have a slightly negative overall Q score, which is quite the achievement. But the really big problem at the moment is that the validation reports can really drastically overestimate the quality of a model. And here I am, well, before I show an example of that, I'm going to do a very brief aside, which hopefully the meaning of which will become clear a few slides later. So go back to ancient Greece. The Greeks assumed Earth was the center of the universe with the heavenly bodies revolving in spherical shells around it, which makes perfect sense. If you're lying there on the ground looking up at the sky, you see the stars moving past you. But it was understandable as an initial assumption, but the fit to observations became increasingly poor when people actually started really following the motions of the planets. So in order to rescue that, Aristotle introduced the idea of epicycles, and that was further refined by Ptolemy. And that model got complicated. But to be fair, if that was taken to the extreme, you can actually fit any orbit with arbitrary precision. And it's actually interesting to consider an alternate version of history where we would be standing here talking about the Ptolemaic transform rather than the Fourier transform, because that's essentially what this actually is. It's just the first few terms of a Fourier transform. Then, of course, 1,500 years later, Copernicus came up with a simpler model that actually explains things with much fewer variables and in a much more sensible way. Hold that thought. So what I'm going to talk about for the next few slides are these two structures, which are very, very, very similar on the face of things. I mean, they're both 2.8 angstroms, between 1 and 2,000 residues, quite recent. Both have nearly identical validation scores. If you look at those headline metrics, class score of 2, Ramachandran outliers of 0, sidechain outliers 1.3 versus 1.2%. Who really cares? They look the same according to this. And actually, if you look at the Ramachandran plot, to be perfectly honest, looking at this, I would worry about the one on the right more first, because that's showing those really telltale signs of refinement with a Ramachandran restraints, where you have this unnatural clustering of residues all around that 2% cutoff. So far, really hard to tell the difference. The Ramachandran Z-score does sort of flag the one on the left as possibly problematic, but it's sort of in that gray zone. One thing I've found previously is often the overfitting problems can really jump out when you start a model moving in a Zolder, where the physics just push these overfitted things apart, and you create new outliers that you can actually see and do something about. In this case, you don't actually get really very much of that either. Most things stay within the contours, and it's still hard to tell. One thing that does start to differentiate, if you really pay close attention, is the Q score. And you see on the chain B of 780K there, those first few hundred residues have an unusually low Q score. But if you were a reviewer and you didn't want to actually go through the process of, as very few people want to do, actually going through residue by residue in this map, you might go back and look at the overview and think, okay, well, we have this, so we have this big region of map up on the top right there that is just very poor. And you could say, okay, that's just this poor region of map, and just wave it past, which is, let's face it, is probably what happened here. One thing that does, I have to admit, really pull this out is Kablam, which I think we should be starting to use more, but it really flags this one as having a large number of outliers. Now, here's the upshot. If I take these things through and do an end-to-end check rebuild in as older as I tend to do whenever I'm interested in working with any structure, the one on the right here, nothing much changes. There's a few tweaks, maybe a dozen peptide bond flips, a few radar adjustments. Things don't move very much at all. It is basically a very good model. The one 780K, on the other hand, is about as lost as I've seen anyone get when tracing. And being totally fair here, there was nothing like this one in the PDB before. This is the first of its kind. But we have, so on the y-axis here, that's the shift of the C alpha atoms on rebuilding. So anything more than about 2.5 angstroms is a shift in register. So that great big peak in the middle is a few hundred residues that are just out by anywhere up to 15 residues. And the validation report just does not tell us. That's a problem, and I think a frightening one. And this is something I stumbled across entirely at random back in 2021. I just like to grab something recent off the PDB sometimes just to play around with something new and is older, see what I can find. At the time, it was a huge pain to actually rebuild that. These days, it's actually quite easy. Start from the AlphaFold model of that chain B, and it actually pops into place pretty straightforwardly. So that's a problem. Now, there's various things you can various. I do want to make it clear here that my point is not to point fingers or embarrass anybody. Model building has historically been really hard, and when you're not used to it, not used to looking at a model in density, it can be hard to say what's a good fit, what's not. And when your refinement comes back with a validation report looking like that, it's perfectly natural to think, okay, I've done it. And when you take that validation report to your supervisor, it's perfectly rational for them to think, okay, you've done a really good job, I don't need to look. And that's how these things get through. Now, in terms of how that happened, it's easy enough to sort of point fingers at things like the overuse of Ramachandran and rodent restraints that are overfitting to these contours. But the more I think about that, the more I think that they're really a symptom of a bigger problem. And ultimately, the problem is that the restraint libraries we're generally using just aren't up to the task. And they haven't been for some time. Now, they made sense. They made absolute sense when they were first developed back in 1991. But back in 1991, this was the cutting edge computer at the time. Cost $10.5 million. 32 billion floating point operations per second, which sounds like a lot if you're not used to those numbers. But that is outperformed about 600-fold by the laptop that I'm doing this presentation on. And theoretically, at least, about 60-fold by an iPhone 14. Things have changed, is the point. Now, the other thing back then is we didn't have anywhere near as good a grasp of molecular physics as we do now. So it's this combination of designing things for the computational power available at the time, combined with the knowledge at the time. It was the simple thing to do was just to do statistical distributions of very local stuff, bond lengths, bond angles, these local observables of what a molecule looks like at that individual atom scale. Now, torsion distributions were added a bit later, and as were the clash terms. But again, the clash terms are a simple direct contact scheme. And ultimately, the problem is these restraints have no concept of physics. And And one really telling example of the outcome of that, this is actually a crystallographic model that I'm kind of pretending is cryo-EM, but forgive me for that. But this is a part of a demo model built into Isolde, or distributed with Isolde from 2015. It's 3 angstrom resolution and really quite typical for its time. And the thing I want you to focus on is this this loop on the why is it not running? The loop in the middle. And if you look at it in the classic view, hello. Okay, I think I'm going to have to. Oh, there it goes. So if you look at this in your classic view without hydrogens, it's easy to go straight past it because it kind of sort of fits the density. There's no backbone outlier there. But add the polar hydrogens and then it starts to become more sensible. You see you've got these amide protons just pointing at each other where they really don't want to be. And in Isolde, now I have to admit, I often worry that this is probably where I lose a lot of potential users of Isolde when they take their painstakingly built and refined model and drop it in. And the first thing that happens is a bunch of new outliers appear and their R factors go up by a few percent. But it's because it's doing these sort of things. It's not allowing these physically impossible things to actually be there. It's pushing things out of density where you can see them and then actually fix them. And these problems are everywhere. And they are ultimately a problem of that underlying restraint library. And most of what we've done since the introduction of reference model restraints, secondary structure restraints, Ramachandran restraints, all of those, ultimately they are kind of the equivalent of the structural biology equivalent of epicycles. They're extra things that we have added on to try and get a better fit to the observations when the real problem is the underlying model is incomplete. And I think it's time that we really started thinking about what comes next. How do we make that better? Now, the problem is the existing MD force fields honestly aren't really the answer, but I think they point us at the answer. But the downside of using physics-based restraints like in Isolde is that they are far, far more costly. The MD people learned over many years that to get a model to behave sensibly in an MD simulation, you have to be summing up all the non-bonded interactions from roughly depending on your conditions, from a 10 to 15 angstrom shell around it. That's a lot of atoms. So what you're looking at here is this sort of region you consider when you're talking about Kleist score. What you see here with with hydrogens added is what you actually have to consider when you're talking full physical treatment. The thing is, modern GPUs handle that easily. I mean, I can't claim credit for that. I'm using the OpenMM library from Stanford for all of this, but on the machine, this machine here, for a 10,000 residue model, you're getting between 300 and 1,000 time steps a second. It's not a problem with modern hardware. And they actually do it really amazingly memory efficiently. Now, you've seen this beast from yesterday in the wonderful Michelangelo talk. 2.5 million atoms, 80 megadaltons in a 3.3 angstrom map. It is truly staggering and actually fits easily on a RTX 3070 GPU. Glacially slow, of course, but the nice thing about especially about cryo-EM is that it's easy to actually break down into pieces, and you don't have to run the whole model at a time, but you can if you want to. And yeah, just down in the bottom corner there, that's insulin for scale. Another way of putting this thing is I think about 10 ribosomes in size. It is truly staggeringly large. So upsides though, if we take that HE99, which to repeat myself, that is a very good model as it stands. It's up there with essentially state of the art, but it is not perfect. There are still things in there that don't follow the laws of physics, and so if I spend a couple of hours going end to end in a Zolder, just fixing up what the force field is saying doesn't make sense, I can take that, well, hopefully the rest of the way. I'm not going to claim that's perfect either, but you can get that clash score down to 0. And it's doing this without any of those Ramachandran radar restraints and anything like that. It's just using that physical force field. With the exception of some safety barriers put in, just because tugging things around with a mouse, you introduce very large forces that you need to protect. But those don't kick in unless the model is already far from its low energy state. So now most of these errors are small and even, well, what most people would quite rightly call trivial, but these often are the things that actually keep me up at night a little bit, because it's that triviality is actually what makes them so insidious. Now, because they don't have any real effect on static structures, people will often say, well, who cares? Don't bother fixing those. We push this through. But what each one of these does, and the example here is this leucine residue, which is in a somewhat disfavored but not outlying conformation in the original map. If you start it in a Zolder, it immediately collapses into a lower energy state, but you actually have to look pretty closely to realize it's the wrong low energy state. It's really poking out the density. You flick it back, then you get something that actually fits the density and is the correct solution. Now, the problem with these is that every time you have one of those, you have this little region around it where everything is pushed out by a few tenths of an angstrom, and you've got this sphere of pressure, of stress, of compressor stress or tensile stress, just pushing your molecule slightly out of the way. And if you're just doing a static analysis, everything else, all the refinement is going to push everything else around to just kind of minimize that. You won't notice it. But anyone who's trying to do dynamics on this thing, you just don't know what's going to happen. Sometimes it'll do nothing, but sometimes, well, you look at GPCR biology, for example, these enormous conformational changes that hinge on tiny movements exactly like this. You don't know the effect. And these are everywhere. These sort of problems are in almost every structure in the PDB. And the thing we should remember above everything else, that 99% of users of the PDB are users of structures, not creators of structures. Most of them will never look at a model in a map, and would not have the competence to actually try and correct things if they did. So these do cause real problems downstream in things like drug design. So now the downside of MD, well, there are quite a few of them. So the current standard MD force fields are limited. Their coverage of chemical space is incomplete, especially when you're talking unusual elements. They are increasingly difficult to extend upon, and they have very small systematic deviations in bond lengths and angles, which is why if you ever take a model straight from a Zolder, and why I don't recommend doing this, and try to deposit it, you'll get a bunch of red flags on angle bond and angle RMSDs, and especially great big red flags on arginines because of this 3 degree discrepancy in internal bond angles. Comes up as a great big outlier. Generally, in the grand scheme of things, not big issues, but it's not something you want to start polluting statistics with. But the good news is that there's some really exciting work going on in modern machine learning approaches to parameterization of models for classical MD that show enormous promise to essentially do away with these problems. And my favorite at the moment is this project called Espoloma, which does away with the idea of residue templates for MD entirely. And instead, you just feed it a graph representation of your model, and it feeds that through its trained network and spits out bond angle, all the parameters needed to represent this model in a physical system. Now, I think, honestly, the more I think about this, I think it's one of the most natural applications of machine learning I've ever come across. It's not ready for prime time use yet, but it seems a very straightforward way to get to where we need to go, because it's the sort of thing that can be trained both on the quantum mechanical energy profile data that classic force fields are trained on, and the high resolution experimental data that gives us all the equilibrium values that we really care about when we're talking about the experimental structures. So it's, the theme of this talk is that I'm mostly talking about problems and only the vaguest hint of solutions, but this I think is one where we should be looking. But the other thing, again, coming back to this one, this is the one that really got me thinking about how human-centric modeling is increasingly untenable. If we do some numbers on this thing, just over 150,000 residues modeled in this thing, and it is at 3.3 angstrom dense resolution throughout most of the map. It's the sort of thing that if you took the time, you could do a really good job with. But the time involved is just insane. Now, when I sit down and really get into the zone in the Zolder, I can, in good parts of the model, I can be just zipping through, but on average, I'll manage like 3 seconds of residue, averaged over hundreds of residues. But I'll last a few hours like that before I get glassy-eyed and increasingly antisocial and generally need a break. This guy, you're talking 128 hours straight work of doing nothing but staring at residues in density. And honestly, to expect any PhD student or postdoc or anyone to do things that way in something like this should get you shipped off to The Hague and tried for crimes against humanity. So we need another way. But the thing is, it shouldn't be any surprise, and I don't think there is any fault to be had here. If you look at the details of this model, that they're really not great. Essentially, anywhere you look in here, you'll find massive clashes, you'll find things out of register. Well, you'll find change that they couldn't identify, as the model Angelo Chiara showed yesterday. But I mean, I am the sort of guy that I once spent a week just going through a new ribosome structure end to end because I was bored in the middle of the pandemic. And yet this thing puts me in a cold sweat. I would not want to do, I would not want to touch this. And if we look at the validation report for this guy, it's 4,700 pages long. And that's not even accounting for the fact that this beast crashed the Clash Score server. And so that part of it is blank. It would probably add another 5,000 pages on its own. We can't do it that way. So the upshot here is that a few things. First thing, I think there is a really urgent and increasing need for a really foolproof, holistic validation, something that takes everything we know about these things. And in particular, yes, it's important to have a reliable validation that points you to the most important part to fix next, so that the most pressing problem. But the bigger problem we have at the moment is that so many of our validation tools have this very high false negative rate, where they're not flagging something that is actually wrong. And we are missing so much because of that. So and I don't think the answer is going to be adding more and more individual metrics and tables that you have to check and tick off every single one, because, well, I mean, yeah. We need to find ways to really take everything we know and condense it into one really clear measure. And I think that is going to be a really clear machine learning problem. But we have a real chicken and egg problem on our hands here, in that what we really don't want to be doing is training on models that themselves have errors in them, because we do that and we just bake in all the problems we have, and they become part of our validation set, and things get worse. So we need a very careful conversation about how we're going to do that. And then the next step, of course, is we need auto building tools that can actually pass all of that without becoming some circular problem where they start doing the same things that Ramachandran and Radhima restraints have been doing, and force fitting to our validation metrics. I think all of that's going to be very challenging, but everything I've been seeing suggest that the path forward is becoming clear. We need to have some community level commitment to say, well, this needs to be done, and we need to get together and do it. So yeah, as I said, implementation won't be trivial, but I think all the current technology we have, we don't need any new technology. We just need to put it together in the right ways. It's probably going to be beyond the scope of any one group, but I think we need to get the community talking on this and start making things happen. And I'll take any questions you have.